Okay, it's 10 o'clock Central European Summer Time. Very welcome and good morning to Europe. I guess good afternoon to Asia, and very early good morning to anyone from North America listening into the live stream. This is the One World Signal Processing online seminar series. My name is Eric Larsson and I'll be the moderator of today's seminar. Our speaker today is Thomas Schön. Thomas is a Bayer professor in artificial intelligence in the Department of Information Technology at Uppsala University in Sweden. And he is a well-known expert on modeling and algorithm development for systems that are capable to learn and act based on data. Hello, Thomas. How are you this morning?
Hello, Eric. Hello. Very good. Very
Great
good.
To have you.
I
think, yes. Your talk today is going to be on deep probabilistic regression. And I think without further ado, we will let you share screen and get started. So please.
Thank you. And thank you so much for the kind invitation. It's good to be here with you. So I'll talk about solving regression problems using deep neural networks. And this is joint work with one of my students here in Uppsala, Fredrik Gustafsson, and a postdoc at ETH, Martin Danelian. Here are a few papers that this talk is based on. So the main message I have here today is that the combined use of probabilistic models and deep learning is more interesting than we think. And I'll try to illustrate this message by formulating and solving regression problems. So the key lessons I take away from contemporary machine learning is that flexible models often give the best predictive performance. So having said that, the next question is, of course, how can we build these flexible models? And of course, you have deep learning, where we use a fixed number of, typically a lot of parameters. And then we also have the non-parametric way of doing the Gaussian processes, where we also do a lot of work. But I'm not going to talk too much about that today. And when we talk about flexible models, it's also important to be quite careful with these models, because they can, as you probably know, be quite deceptive. And we have seen quite a few examples of that during the pandemics, I would say, but I'm not diving into that more here. So let me give you an example that I've been working on, a very applied problem, just to get started. So this is an example of a typical deep learning problem, I would say. So I'm using this to contrast with what the main part of the talk will be on. So we're looking into spending quite a lot of time together with cardiologists on this well-known problem of automatically classifying and understanding ECG data. So measuring the ECG, electrocardiogram is measuring the electrical activity of the heart. And from that, we can then see, or medical doctors, I should say, can see quite a lot in terms of potential problems like atrial fibrillation and tachycardia and so on and so forth. And what we have looked at is to use a pretty standard deep learning model to automate this task. And this, for us here in Sweden and in many other countries, that's not strictly necessary, because we have humans capable of helping us very nearby. But we're doing this together with friends in Brazil, and they have quite a different situation, where people can have a very long distance to the hospitals. And that's why they built up this telehealth system, which provides us with all the data for this problem. So we have almost 2.5 million ECGs to train on. And we are reaching human level performance. So we are on par with trained doctors on solving or classifying 6 of these problems. And this is something that we published last year And the key difference, as most of you know, is that the model is now not derived by people like me trying to mathematically come up with, or in a clever way, come up with a model based on what I think we see in the ECG. Instead, a generic model is automatically learned based on data. And the key innovation here is actually, as usual, to use a lot of data on a very specific task. We're now moving, we have similar results for 66 of the most common problems nowadays. Okay, so this is classic in the sense that the output here is a class, it's a classification problem. But what about regression problems? How do we deal with them? So let's be very concrete. And walk you through something that you have seen before, I think. And if not, that's no problem. We'll do this gently. So looking at the model that's commonly referred to as a nonlinear autoregressive model with exogenous inputs, so a NARCS model. The idea there is to assume that the output, y of t, depends on the previous outputs that you have and possible past inputs as well, which are called u here. And the goal, if we want to solve this in a probabilistic sense, is to find the distribution, the conditional distribution of the output given all the previous data, which are referred to as xt here. And the challenge here is if you want to do this, how should we choose this predictive distribution? This straightforward option, I guess, is to assume a functional form for this distribution. So if we continue down that path, it gives rise to, I guess, at least two questions. How should we parameterize this distribution? And then once we've decided upon that, how should we learn it? How should we estimate the parameters from the data? So the most common answers to these two questions are to assume an output equation form model. Or it's at least one very common way of doing this. So we assume that y of t is some function, nonlinear function, f of xt parameterized by some parameters theta. And this means that implicitly the solution is now dictated by the assumption that we make on the noise here, E. How should you learn the model? Traditionally, we make use of maximum likelihood. So for example, if I assume that the noise is Gaussian, then the maximum likelihood problem boils down to this nonlinear least squares problem. So a question for you now is why not use a more flexible model? I mean, here we have said, again, fairly implicitly, I guess, that the solution should be Gaussian, whereas we know in many examples that is not true. So this is the starting point, and this is where I started thinking roughly, I guess, 2-3 years ago now, that this is a bit strange. We are not, even if we use a deep neural network, whatever fancy thing we have for this f, we have sort of we still have the problem because we are restricting ourselves to Gaussian. So do we have to do that? The answer is no. Let's have a look at that. So that's the aim of this talk is to think a little about how we best can formulate and solve regression problems using deep learning. And we're going to apply this and try it out on various problems from computer vision, regression problems from computer vision, like this tracking problem, but I'll return to that. Okay, so doing regression with deep neural networks, what is it all about? Let's just be formal. So we're trying to predict a continuous output or a target y from some inputs x, given a training set that is available to us. So x and y's, just standard supervised regression. And a deep neural network is a function f that's parameterized by some parameters theta mapping an input to the output. And again, with a probabilistic take on regression, the task is now to learn the distribution of the output conditioned on the input. So this is the problem. And I give you a preview of the construction that we've come up with so far, which is a general method which has a clear probabilistic interpretation. So we use the so-called energy-based models that has been quite popular for a long time in different settings. I'll come back to them if you haven't heard about them and define them. This is a way, fairly straightforward way of allowing for a highly flexible target density that can be learned directly from the data. So we can do away with this Gaussian assumption. So here is a little toy example just to illustrate that we can actually learn multimodal and asymmetric distribution. So it's in that sense a flexible model. So if the distribution looks like this, you have the x-axis down there and the y-axis here. So two modes here and the skewed Gaussian here. So if you start as in the standard way using a Gaussian, of course it becomes problematic. Whereas if we use a more flexible one, like the one I'm going to talk a little bit more about now, we end up with a distribution that is more akin to the ground truth. Okay, so with that little introduction / preview, let's see how we can do this. So first, I'm going to walk you through what is typically done in when it comes to solving regression problems and deep learning. So broadly classify that into 4 different classes of existing methods. And then I'm going to introduce the energy-based models if you haven't seen them before, and then say a few more words about the construction that we have and show a few experiments towards the end. So again, deep learning for classification is quite standardized in terms of a bunch of losses and representations that can be used. But interestingly, at least as far as I understand, that when it comes to regression, the situation is quite different. So in fact, the current standard practice involves the use of very simple unimodal distributions. Either this is explicitly or implicitly, as I tried to sketch in the beginning there. And the 4 different approaches that I'll walk you through are the following ones. Let's start with what we refer to as direct regression. So here, this is the way I used to think of using deep neural networks for regression. So we train a neural network F to just predict the target or the output. And the way we do this is by learning parameters theta that minimizes a loss function that somehow measures the discrepancy between the prediction that we have and the real measurements that are available. So quite standard. And commonly we use the L2 or L1 loss or of course other choices. Okay, so that's all good and fine. But minimizing and minimizing this corresponds to minimizing the negative log likelihood for a specific model of the conditional target density. So for example, the L2 loss corresponds to a fixed variance Gaussian model. So whether you think probabilistically or not, it's always the case that we make an implicit assumption by using a certain cost function. And of course, restricting this predictive distribution to be a Gaussian is not necessarily a good idea. The second class of methods sort of continues along that understanding that and say why not explicitly make use of this probabilistic perspective and try to at least introduce some flexibility into these models. And what people have done there is to stick with the restriction of a parametric model that is unimodal, such as Gaussian or Laplace. But then we let the parameters of this model, I call them phi here, typically depending on the input, be given by a deep neural network. So this is definitely an interesting step in the right direction, because now we can have a Gaussian with a mean value and a covariance that depends on the input. Sort of the same thing that's done in a variational autoencoder, which is a super interesting and fairly recent example of the combination of a deep neural network and a probabilistic model. And then we learn the parameters by minimizing the log likelihood typically. So again, one-dimensional Gaussian model will look something like this, and the deep neural network is trained to output these two values. And we can write down the negative log likelihood and just push on, so to speak. But again, so this is again one step forward, but we're still restricting ourselves by using a parametric family here. So then there's something that popped up in the computer vision literature a few years ago, which is referred to as confidence-based regression. So this is quite specialized methods, I would say. And what they are trying to do is to train a network that predicts some kind of confidence value that is then maximized over y to generate the prediction. So the key thing to take away from this approach is that the network depends on both the input and the output, not just the input. Challenge with this, so this is very fluffily described here, but the problem with these methods is that when you're training them, you need to do all sorts of ad hoc decisions. And again, if you do them well, you can get really good performance, but it's quite painful to work with them. The fourth class is to sort of give up, I guess, and just discretize the output space into finite sets and then use standard classification techniques, which of course is quite problematic, especially in higher dimension, and you lose the ability to use correlations in between different classes that are straightforward in the regression tasks. That's probably not to be recommended. So what we took away from looking into these different approaches is that these confidence-based regression approaches that I fluffily described, they give really impressive results, but again, it requires very important and very tricky task-dependent design choices to be made. So it's not really an ergonomic method to use. And it typically lacks a clear probabilistic interpretation as well. At the same time, probabilistic regression approach is straightforward and general, but again, it can usually not compete in terms of regression accuracy when you compare to the confidence-based approaches. So we're trying to do a little bit of both here, but we're removing the problems at the same time. So let's see how we can do that. And the key construction are these energy-based models, quite popular in physics, but also in machine learning for other tasks. Recently, it's been used quite a lot for generative models in an interesting way. So the idea is very simple. We're looking for a distribution, P of X. And one way of doing that is to just say, well, we have some general function f, and we look at e to the power of f, and then we normalize that to make sure that this object integrates to 1. And since it's e to the power of f, it's always greater than or equal to 0. So this will be a PDF. And then we can parameterize this function, scalar function, in whichever way we want, for example, using a deep neural network. And then we have the ability to describe much more general distributions. We do not have to come up with or restrict it to a specific family. So in that sense, it's a kind of a non-parametric description. And here are a few references to where this model has been used in the past, just to show that it has quite a long history. Okay, so this is both good and bad in the sense that it's of course a bit more challenging to work with this model. Let's see what that entails. On the good side is that we can work with multimodal or asymmetric densities, and if we have enough data, we can learn them from the data. The cost of doing this is that this normalization constant is intractable, so there is no way we can come up with a closed form expression for this integral. And why is that a problem? Well, it becomes a problem to evaluate the conditional distribution, and it becomes a problem to sample from it. And the problem of evaluating it, well, sampling, you could say, well, maybe you're not interested in samples, so it doesn't matter, so that's okay. But this is typically going to be problematic, because setting up any learning method, you typically have to evaluate the cost function at least, and also its gradients and Hessians if possible. Typically the dimensions are quite large, so Hessians becomes tricky. But definitely the cost function and its gradients we need. So what are we going to do about that? So let's see, there are a few things that can be done. So again, what this construction offers, it gives us a clear probabilistic interpretation in the sense that we learn a distribution P of y given x without requiring it to belong to any particular family of distributions. And the deep neural network that we employ maps an input-output pair to a scalar value f. So that's the way the deep neural network comes in. And we define the following flexible model as a conditional energy-based model with both the inputs and the outputs. Okay. So the training part is to basically figure out the deep neural network that we need. And again, the most straightforward method to do this is the negative log likelihood. There are several other methods. I'll briefly mention one for now, but there are definitely more. And we did a systematic study of 6 different approaches to this, but I'm mentioning 2 of them here. So minimizing the negative log likelihood, of course, we then end up having the integral in here, which we refer to as z. So that's problematic. So what can we do with that? Well, one thing we can do, which works extremely well when the dimension of the output is low, say around less than 10 or so. We can probably get higher as well, but for now, let's think of that. So the problem, we just recall the equations up here from the previous slide. So one way of doing this is to use importance sampling, which works surprisingly well for this problem, actually. So how does importance sampling work? Well, it's a great method for evaluating integrals that relies on stochastic sampling rather than trying to grid the space. Gridding this space in 10 dimensions is not a good idea, whereas using random numbers would typically works better. And the idea, for those who haven't seen it, is the following. It's a very simple idea. So again, the negative log likelihood you have up here, and then I'm just multiplying and dividing inside the integral by some function q here that depends on the outputs. Possibly it could depend on the inputs as well, which typically does, but doesn't really matter here. And the game is the following. If I then, so q, I decided on what that was, so it's available to me, so I can generate samples from q. And then I can just insert those samples in here and get an approximation of the integral in this sense. And what we're doing is we're using a Gaussian mixture for this q function, which is commonly referred to as a proposal distribution, which are centered around the measurements. And then quite small values for m is enough to get a decent estimate of the log likelihood. And since we're typically using stochastic gradient methods to train deep neural networks, the problem is already stochastic. So the fact that we introduce some additional stochasticity here really doesn't matter. And importantly, it does not change the optimization that comes. So this is one way of solving the problem, quite quickly sketched here, but these are the main parts of this solution. Again, the downside is for higher dimensional outputs, this becomes problematic, not in theory, but in practice, because I'm going to have to use a very large M here to get it to work. But again, for the computer vision tasks that we have looked at, which involves object detection and tracking problems, then the dimension of the output is typically quite low, so that's not a problem. Another interesting idea that is quite new to me, at least, is something called noise contrastive estimation, which is a method to compute estimates of parameters that avoids computing the normalization constant and its derivatives. It's a bit more than 10 years old, came up in this nice paper. So what it does instead is that it's, in one sentence, I guess, it's trying to learn to, or it learns to discriminate between observed samples from the measurements, and samples drawn from some kind of noise distribution. So here is two examples. Here is an aircraft, and the sample is this bounding box here. And then here are a bunch of disturbed, where we've added noise to this. And then the method is trying to discriminate between the true one and these ones. So that's the, again, a rather fluffy description, but in just one slide on what this method is trying to do. And we looked into using this method when we compared 6 different ways of training this model. And a modification of this one actually came up on top. So it's doing something interesting. Okay, let's say that we have now trained the model and we have it available. Then what you want to do at test time is, of course, to predict with the model. And the way we do that is to, given some test input, we predict the output by maximizing this marginal distribution. So this is then a potentially quite a big optimization problem. But luckily, most of this work has already been done in the training phase. So everything, the gradients are available quite straightforwardly. So there's not a big computational overhead of actually doing that. And then we're just using gradient search to find a local maximum, starting from some initial estimate. of course, all the standard problems with local search applies here as well. Okay, so let's have a look at a few concrete examples. So the first one, I think I have two examples here. There are more. If you want more, you can look into this paper where we also provide thorough evaluations, which I'm not going to dive into here now. But when it comes to the computer vision problems that we look at, let me just mention the ones that I will not talk about here, but there's like age estimation. So from a photo of a person, the task is to come up with an estimate of the age. So that's clearly one-dimensional continuous output. So it's a regression problem. And we've also looked at estimating the orientation of a head in images as you move around. So then it's typically 2 or 3 dimensional outputs, and some and the one I'm going to talk about here is visual tracking. So the task is, in the first image, someone draws a box around the object that you want to track, and then the algorithm needs to spit out the corresponding boxes as the object, in this case, a dog playing around with another dog in the snow. So it's clearly a rapidly deforming object. So let's have a look at a few movies just to see how the estimator is doing. Here, it's not a dog, but it's BMX riders. So the red one is our tracker and the green one is a previous state of the art. Doing quite similar here, but then after a while, the previous one loses track completely because the representations are not good enough, whereas we can still keep following the correct object here. So I'll pause there, and then you can say, well, that's just one sample, and that's very much true. That's why in the paper we run through quite a few videos on the standard data sets for this task, and you can report the figures. Here is another example of this guy running around, a rather shaky camera as well, which makes the problem a bit more challenging. Maybe I should say also that the output, so the Y, is quite low dimensional in this example because it's just the X and Y position here, and then it's a width and a height. So in that sense, it's 4 dimensions. So that's quite low. So the importance sampling works nicely here. Okay, so that's that problem. Then we switch to another sensor. So now it's laser data. And the task is to detect and track objects. Here it's now in 3 dimensions. So we have each object is described by this quite simple geometry. So just an X, Y, Z position, and then there is a width and a height and a length. So it's now 6 dimensions. Still a low dimensional problem in that sense. The input data is, of course, very high dimensional because this is one of those 3D lasers on top of a moving car. And the reason why you want to do this is, as you guess, an important perception task for any self-driving vehicle or robot. And again, shows you, I hope, that combining deep neural networks with probabilistic models is, at least according to me, very exciting and quite promising. And I foresee quite a few new constructions coming up along this line. Let me show you what this looks like when we run it. So maybe I should pause first and explain what you see. So this is what the driver sees, and then the outputs of the regression problems are just reprojected onto the camera feed. And the same, this is what the laser sees, and the regression outputs in terms of point estimates are displayed. So as we keep driving around, we get decent estimates of the other vehicles. Let me pause that there. Okay. So what we're currently doing along this path, a few things, but one thing that's more or less done is that it's a bit annoying with this proposal distribution, since it has to be designed manually. So what we've done now is we've been able to automate that by borrowing from another area where I've been active for a long time, which is sequential Monte Carlo methods. And there we have seen interesting developments in automatically learning suitable proposals. So we sort of use the same high-level ID, but in a different way. Applied it to this problem, which not only improves the results, but it also takes away some of the tuning tasks from us when we're implementing this. And this should be an archive sometime next week, I hope. Finishing off a little bit early, but hopefully that's okay. Just want to do a little commercial if you're interested in machine learning. So we recently, or over the past 5 years or so, we built a course designed for engineers and scientists that we built here in Uppsala. And in doing that, we ended up writing a book because it was interestingly missing, despite the many books that are available on machine learning. So this is being published by Cambridge University Press. It should be out I think within a month or two. In any case, it's freely available and will continue to be freely available on this website. And all the material for the course is also available if you're interested in that. So the difference between our book and some of the existing ones is that we're focusing more on the principles than on the specific algorithms here. All right, so to conclude, what I tried to do in this talk is to create some kind of awareness that we can use deep neural networks to solve regression problems, not just in the standard way, but perhaps using these energy-based models can be useful. So we introduced them for regression. It's a generally applicable construction, even though I showed you some specific application examples here, and solved the training problem using importance sampling and a version of noise contrastive estimation. With that, I think I should stop and see if there are any questions. So thanks for listening.
Thank you, Thomas. Really exciting and inspiring talk, I think. Well, it's hard to give you an applause, but I'll do like this. Anyways, thank you very much. So we'll be happy to take questions. I think either or preferably if you write questions in the chat. We could also, if anyone has a question, just turn on your camera and microphone. But I think we'll probably start with the questions that we have received in the chat. And let's make sure I'm reading correctly here, but there is one question on slide 24, where, Thomas, you mentioned an example of object detection and tracking. I think the question is to give more explanation with regard to it. We might have to go back and see what was on page 24. Right. So I'm sure the question here states that you mentioned an example of object detection and tracking. Please explain more with regard to it. I'm not exactly sure what in detail is meant here.
No, that's
maybe
hard to see from this slide, I understand. But let's keep this slide anyway, because this shows a bit of the cost function, at least, that's involved. And then later on, I talked a little bit about the tracking problem. So let me just skip over there. Just to remind you, so the tracking problem here is now this dog moving around. So And a human being puts the first bounding box, so this blue dashed box around the dog. And the output, what the algorithm needs to do is then to keep outputting this distribution as we go. And what is plotted up here, this I did not mention, but that's probably good to mention now that we talk about it, is the two-dimensional distribution of this point. So the estimate of this point. We're also computing estimates of the height and the width, but that is not visualized in any other way than the boxes here. But here you can see a glimpse of the fact that we have a probabilistic version. And at this stage we are starting, so nothing is happening. But here you can imagine that this dog is moving in this direction, right? So you can also see that we have most uncertainty in that direction. Whereas here it's turned around a little bit, so then the uncertainty is more in this direction. So you can, it's maybe not the best attempt, but we tried to get some of the uncertainty into the plot here as well. So if we move back to slide 24 and we look at the cost function here, then the y's here is again this four-dimensional variable, and the inputs x, that's just the images. So that's high dimensional in the sense of the number of pixels, I guess. But again, importantly, this does not enter the integral, so that's not the problem at all. I'm not sure if that answers the question.
Yeah, I think it probably does, or in case it doesn't, then I think whoever asked the question would have to come back here with more detail. So thank you for that, and I'll be moving on through the Q&A to the next question, which is on the structure of the DNN. So the question is, could you give more details on the network structure of the DNN? Any specific network structure devised, or just a fully connected DNN?
Yeah, that's a good question. I did not say anything about that. And it's not just a fully connected DNN, not at all, actually. At the same time, we haven't really been too creative in the structures, I would say. So for example, for this problem, we relied on available network structures that has been developed for similar problems, I should say. And then we adapted them, of course, so that they could fit into our formulation. But this is, so my student has some former understanding of this problem. He worked with that during his master thesis, which was helpful. So that combined with existing networks is more or less what was used here. And if you want to dive into the specific details, then you can look at this paper, which is also available on arXiv, which details that. But it's a good question. I mean, just using a dense network will not give state-of-the-art results on these applications. So we need the craftsmanship of network architectures to push the performance here.
So it's like you build upon structures that are known to be good for this type of applications.
Precisely.
Yeah. Very good. Okay. So next question here is, have you thought about using variational inference to deal with the interactable integral? I have a feeling that you might have thought, okay. Yeah, go ahead.
Yeah, that's one thing that we have looked into as well. And in the interestingly, in coming up with automating the proposal construction, we're using a variational approach, actually. And this is something I find theoretically a bit appealing, because, of course, with variational approaches, we can never get to the true solution. But we get surprisingly good results, I must say. I mean, it's a really good way of doing it, and it's typically fast. But by putting a variational solution inside a Monte Carlo algorithm, you get you get a bit of both if done in the right way. So you get a fast solution via the variational approach, and then by putting that into, in our case here, importance sampling, we get some theoretical guarantees, which I think is nice from the theory point of view. So we know what the construction is actually doing, and we can prove things. But of course, that using variational approaches straight off is also an option, which we should probably look into a little bit more.
Right. So yeah, very good. Thank you for that. So I think there aren't any. Oh yeah, so here's another question just popped up. Have you thought about using Bayesian neural networks to replace the DNN for f theta of xy in this EBM or energy-based model? What would be the benefits and challenges?
No, we have actually, well, we have sort of discussed it, and the thing, it came up, but we have not, honestly, not really tried it. I think that's also interesting and would be worth pursuing. In early work, we played around a little bit with these ensemble constructions that does quite well, actually. But again, for this application, we have not tried it, not because it's not interesting, just because we simply haven't had the time to put priority to it yet. So I think that's a great and very natural idea.
Yeah, good to know. So and then there's a next question here on complexity. So what about the sampling complexity compared to state-of-the-art algorithms?
Let's see, sampling complexity, you mean in terms of?
Well, I would think that I was asking, the question here is referring to, like, now you compared at the end your algorithm with a state-of-the-art algorithm, right? So I mean, could you comment on like the computational complexity of training and actually running the algorithms?
Yeah, good point. So computationally, the differences are not major. It's not like this way of solving it is much more expensive compared to earlier approaches. From the top of my head, I don't have the exact details here, but again, not a massive difference in any way, which I'm quite happy with, actually, given that we're using Monte Carlo to compute an estimate of the integral there, but still that runs fast enough.
So comparable, more or less, then.
Comparable,
yeah, great. So I don't see more questions in the chat window here. I'm not sure if I could ask a question. I was trying to understand better, like the intuition for, if you go back to, I think you had on page 20 as the first time you introduced the EBM, and you postulate that this parameterized probability density then is the exponential of the f theta, and then you learn the f theta. So what is like the intuition or the basic rationale for using the exponential here? I mean, you could think of like any functional mapping, right, from f theta to p. Is that the only way of doing it, or the best way of doing it?
No,
could you like comment on that? I think this really traces back also to, I mean, things you said earlier. I think you said even on like page 16, if you go back, you talked about in the background this discussion here about learning, training a DNN to estimate the parameters of a Gaussian model, right? And then you parameterize the model through the mean value, the mu, and then the variance, but the variance in the log domain, which is, I suppose, just one possible way of parameterizing. You could do something else than taking the log there, right? I mean, you could just keep the sigma, I suppose, or put some other function of the sigma. So could you comment on like the pros and cons and possibly alternative ways of using other functions in this context?
No, that's a very good question, I think. So for back here, there is of course nothing forcing us to use the exponential here. it's a bit, I'm guessing a little bit now because I've not been in that particular area for too long, but like the exponential family of distributions has been around, and then this is close to that family. So that's my best guess.
Right.
So of course, any function that is positive would work.
Right. Yeah, I can see that. I mean, that it's a natural way of handling distributions that are in the exponential family, right? But on the other hand, I suppose there might be other distributions that aren't in that family and that could also be relevant here. I mean, for example, if you have a lot of outliers, then you might want to use something like symmetric alpha stable or Cauchy or something else, which don't have that form. But okay, so I think in the meantime here, there were a few other more questions that appeared in the chat window. So let's see if we can return to them. There's one here. Hi, and thanks for a nice webinar. In light of Kenma's question, the normalization factor, also known as the partition function, I suppose this refers to the denominator in your PDF, right? So this factor can be tractable in terms of some specific optimization problem, for example, the worst case method. Is that correct? Meanwhile, could you go over some game theoretical issues in this problem? Yeah, that's the question, the way it reads.
Let's see. Yeah, there are definitely models where we have explicit expressions for the partition function, but again, these are quite restrictive cases. Then we fall back into having to make assumptions that we typically don't want to make, like linear and Gaussian, for example. Yeah, I guess there are others as well that will give us a tractable partition function. But again, we don't want to do that, because then we lose what we are trying to achieve here. And going into some kind of game theoretic, I'm not sure exactly what you're thinking there.
No, isn't obvious exactly what I'd refer to, but yeah. Right, so let's see, we got a couple of more that popped up here right now in the chat. So I think this is a clarification of a previous question that related to sample complexity, and it states, actually my question is, what would happen if we reduce the amount of training samples provided to the proposed model? Would it be more sensitive or not than state of the art?
Yeah, okay, now I see your question. Good. Yeah. So we definitely rely on having quite a lot of data available, since it's a deep neural network that will suffer if we reduce the amount of data. But again, the competing methods also rely on using deep networks. So while we have not really tried this, but my guess is that there is no systematic. There will be a difference, definitely, but I don't think it will be a very systematic one, at least. But it's a good question that we should really look into, but haven't done. But again, my guess is that probably not. Sometimes we win, sometimes the other win, but that's my best guess.
Yeah, so no like systematic and significant difference between them here. There is an additional question that just came out here also in the chat, which I think might refer back to something asked earlier, but the question, the way it reads is, can we relax the aforementioned function in terms of self-gravitation oscillators?
To be honest, I don't know exactly what the self-gravitation oscillator is.
So. Neither do I.
So
I'm not quite sure what's meant.
Hard to answer that question.
Yeah. I also did not understand it. So,
but I mean, if I freely interpret what you're getting at here, we can definitely do other types of approximations. So I mean, here we have said here this integral, and it's not tractable, so we need an approximation. And then I walked through a very specific type of approximation. We can of course try other approximations, and what's better or worse that depends as usual. But it's not like you have to approximate it the way we did here. Not at all.
Right. Yeah, I think perhaps that's what the question alluded to, right? That certainly there might be other approximations that could be applied here with similar potential better result in those. Great. I think we went through and covered the questions that appeared in the chat. Does anyone else among the audience want to ask a question live? Then you could raise your hand, I think, and I could give you permission to turn on your mic, I believe. If not, then I think we are approaching the close-up here. So it's been really, I think, a great talk, Thomas. Thank you very much. We also had a great discussion, I think, afterwards. So thank you so much for being with us and doing this. And
yeah, of course, my pleasure. Great to see so many people and all the discussion. That's great. That's fantastic.
Indeed, it was very, very good. So thank you so much, all. And I think that's it. Yeah. Bye-bye.
All right. Bye-bye.